couple things, well, one thing before starting off, there will be no problems that due this week. I'm sure that's a hardship on all of you, right? You know? Strange world where less is more. All right, so the next problem set will be due a week from Wednesday. Couple things that I left behind sort of in the world of LEDs. Just wanted to say 2 cents about it before going on and look at how lasers work. I introduced the idea of a semiconductor in the context of silicon, which is the classic semiconductor for a lot of your electronic devices. It turns out silicon doesn't work for light-emitting diodes themselves. It's not good at radiating light when electrons go from the conduction band to the valence band. So all the LEDs are made of more exotic materials, ones that aren't normally used for computers, but are suitable for light-emitting diodes. And one of the most recent, you're mostly too young to know that blue LEDs were sort of the holy grail. They've had red and green for a very long time, but blue LEDs are recent, or relatively recent. And you need them to, if you want to make full color displays, you need red, green, blue, right? So once they managed to get the right semiconductors working for blue, that changed a lot of display technology, because now they can get all the colors. So that's one thing. The other thing is I didn't talk about white LEDs. The brightly colored LEDs are pretty straightforward. You choose a semiconductor that has a band gap, that is the energy spacing between the conduction band and valence band, that corresponds to the photons you want to create. So if you want a red photon, you use a little band gap. You want a blue photon, you want a big band gap. White is a mixture of colors. So how do you get that? Well, there are two approaches. The high-tech, sophisticated one is to combine 3 LEDs, to have a blue LED, a green LED, and a red LED. And there are systems that do that. And those systems, in many cases, you can adjust the brightness of the red relative to the blue, relative to the green. You can actually tweak the color. You can get different whites. Or if you really want colored light, you can just turn off some of them, and you can get red light if you want. The way that most colored LEDs work, white LEDs work, it's a cheat. They make an ultraviolet LED, which also exists, or at least very, very near ultraviolet, sort of violet, ultraviolet, right on that edge, and then they illuminate a phosphor, like the fluorescent lamps, and the phosphor glows white. So they make the high energy photons, and then they pass those off to the phosphor and let the phosphor absorb and re-emit the light, having chopped off some of its energy, its thermal energy, and toned it down into the visible spectrum. So that white LED is an ultraviolet LED making a phosphor glow. All right? Works fine. Any other questions about LEDs? How LEDs work? All right, I'll leave them behind then. And go on to talk about lasers. So we've been getting more and more sophisticated light sources, and now sort of the ultimate sophisticated light source is a laser. And what distinguishes laser light from the light from all the other sources is that it's one giant wave, or approximately one giant wave. Now, what's that? Why does that distinguish it from anything else? Certainly with the light sources, the sun, it's buckshot, I described it as. That it's lots of little waves, all of them independent, all of them a little different, all of them heading their different directions, different wavelengths, they're just off they go. And every one of these waves carries with it, it's as small as it can be based on quantum mechanics, as little energy as it can be based on quantum mechanics. So it's lots and lots and lots of little waves. Same is true for LEDs, discharge lamps. All the light waves are sort of as small as they can be and still obey the laws of quantum mechanics. I told you that the smallest unit of, for example, red light at a very specific frequency is 1 photon of that frequency, one little packet of energy. You can't make half a packet or 1.5 packets. You only make one or not. So anyway, there are lots of little packets. Laser light's different. Laser light is one giant wave in the sense that it does carry with it, it is composed in effect of photons, but all the photons are identical. So they work together as one enormous wave. The characteristics of the wave can be very complicated, but it's one giant wave. The way a radio wave transmitted by a radio station is. So the transmission from a radio station, when they're just, say, an AM station broadcasting quiet, they're just pushing charge up and down their antenna, up and down, creating one enormous electromagnetic wave of very long wavelength, very low frequency. Off it goes, electric field up, electric field down, electric field up, down. If you get into the details, it's carrying packets of energy, those photons. And there are a fantastic number of them, but they're all together in phase and character. They're all going together, and they create one enormous wave. You barely notice that it's got any quantum character at all. It's described, and I introduce it classically. That is the opposite of classical physics. Is physics before quantum mechanics, and also in some contexts before relativity. So a radio wave is sort of a classic wave. Who knows? You wouldn't even notice there's anything quantum about it. If you go carefully, if you really, really dig, you can find it's got quantum character. What about laser light? Laser light is very much like the radio wave. One giant wave composed, if you want to go into detail, of lots of little photons all working together to create that one giant wave. It is created differently than a radio wave. Radio wave, you can produce this organized giant wave by shoving charge up and down an antenna in an orderly fashion. To launch a light wave like that is just too hard. You can't just yank charge up and down that fast. Light waves are too high frequency, too short wavelength to pull off that stunt. So to create one of these giant waves where everybody's working together, you have to use an amplification process. And laser, the word laser is an acronym, whether you may or may not know that. It stands for light amplification by stimulated emission of radiation. That name was based on a name that was predated it called the maser, which was microwave amplification by stimulated emission of radiation. So the laser was invented about 1960, give or take, and they carried over that acronym from maser to laser, and it really is a stimulated emission process. And so I have to talk about how that works. This stimulated emission means that you start with one initial wave, and you then duplicate it over and over, and that's how lasers generally produce their intense single wave. Okay, so what's the story here? Normal emission of light is called spontaneous emission. If you look at, for example, at a neon atom where one of the electrons has been promoted into an excited state, one of the states it would not normally, in an orbital it would not normally be in. So it's got extra energy, and it can return to an orbital that it would normally be in by emitting energy, by releasing energy. It undergoes what's called a radiative transition from the upper orbital to the lower orbital. And in doing so, it creates one photon of light carrying the energy difference between those two orbitals, and off it goes, typically red light. There are a couple other possibilities, but most of it's the red light of neon. That transition is a little peculiar in that the upper orbital, when the electron's in that, at the simplest level, it's in a standing wave that it's very happy in, and it would stay there all day, and sort of forever. If it's in the lower orbital, it would stay there all day too. Why does it even make the transition? Well, the process of making the transition, it gradually evolves from having a lot of presence in the upper orbital to having a lot of presence in the lower orbital. It evolves, and that evolution involves a net jiggling of charge, up and down, which is what radiates the light. So if you look deep into the quantum mechanics of going from one of these upper excited orbitals to lower orbitals, it involves a rhythmic motion of charge suitable for accelerating charge radiates light, so off goes the light. And what gets it started in this rhythm? Well, it's quantum fluctuations. The world of quantum mechanics is rather interesting. It's complicated and messy, and it's got things in it that you wouldn't expect, like things are always fluctuating around. Nothing's very still. Even empty space is actually a busy place. Empty being like you've removed everything you could from it. It's not completely it's not completely empty then. It's still got some quantum action going on. And part of that quantum action that just lives in space is what triggers this transition from the upper orbital to lower orbital, and off goes light. And that triggering process is called spontaneous emission. It's got a randomness, some real randomness. Einstein was very resistant to the idea that the universe has randomness in it. And he's wrong. The universe really does have just pure random character to it that you cannot predict. It's not even defined what's going to happen, which way the light's going to go from a neon sign. You turn on the neon sign, and you got an excited atom in there. No one can know which way the light particle is going to go. It's not defined in advance. It gets triggered off spontaneously. But anyway, it's all every particle goes off on its own, and that's spontaneous emission. Each time it happens, it has nothing to do with previous emissions. Everyone for themselves. So I've got incoherent radiation. The word incoherent means that describing it as a wave. If you've got multiple waves, multiple atoms emitting their photons, they're so unrelated, those photons, except maybe they share some similarities. They're sort of the same color, or nearly the same color. So there's no overall coherence to them. They're just disorganized. And so it's called incoherent radiation. All right? That's most of light. I actually asked you this question. If you split the beam of light from a flashlight into two beams, this is leading up to something. So you take a flashlight, just ordinary flashlight. You split it into two beams, overlap it. Can you see interference effects? Remember, interference effects are when a wave split into two pieces overlap in a way such that they experience things like the two electric fields are working together. You get a constructive interference. They're working at cross purposes. You get destructive interference. You see nothing. So do you see interference effects? I've got four choices. Yes, because the beams are part of one light wave. How many think that? No, that's why I just told you that most light, it's not one big wet light wave. It's a lot of little ones. And yes, because beam contains many waves. And let me make sure that was the question. That was the answer I wanted. Yeah, that's the one I wanted. Yeah, terrible question. Who wrote this thing? Me. It does exhibit interference effects. We've seen some of those. For example, I showed you that when you shine light off a soap film, you see the colors. It breaks out the colors somehow. What you're seeing there is interference effects, but it's every wave interfering with itself. So this is spraying bazillions of little wavelets, little photon waves at the wall. And if you're going to get interference, which you can get, it's between one of those photons in itself, one of those little waves in itself, which gives you really wimpy interference effects. Because if you send a million of these waves against the wall in a second, and each one the only thing it can do is interfere with itself, well, it'll give you some interesting interference effect on the wall, but the other wave has to interfere with itself, and it might have the same interference effect, or it might have different interference effect, and then sort of wash out the one that was from the first wave. So they don't work very well together, don't give you very good interference effects. So in the era before lasers, interference effects with light were kind of wimpy. You could get them, but not often and not very dramatic. And that's why sort of asked the question, although I regret having asked it as a question. All right, what's the alternative? The alternative is what's called stimulated emission. And if you look at something like neon, where it has an electron in the upper, in this excited orbital, and that electron wants to shift into a lower orbital, it can do it spontaneously, and it will. If you wait long enough, it'll happen. It'll drop down, and off will go its photon slash wave slash particle in some particular direction. But what if passing by at some moment, while it's ready to try to emit light, if what passes by is another photon of light, just right, the same as what it wants to emit. So you've got an excited neon atom ready to emit light, and if a particle of that favorite light passes through the atom, there is a possibility that the atom will duplicate it. Why? Because the passing light wave does have an electric and magnetic field. The magnetic field, not very important. The electric field, important. It jiggles the charge. It actually distorts the orbitals of the neon atom, and it initiates the radiation process. That's the same kind of process it's related to the process behind spontaneous emission. Spontaneous emission is these quantum fluctuations triggering the release of a photon. In this case, it's not quantum fluctuations. It's actually a quantum, a wave already intact, already launched, coming by and triggering the emission process. So this is called, instead of being a spontaneous emission, this is a stimulated emission. Yeah, John. How can you tell what energy, what initial photon basically to send through to bring out this stimulation process? Well, often that first wave comes from another neon atom. You can send it in as a seed. So there are lasers that start with a seed portion of light, carefully crafted by some device that makes one wavelength, sends it through a bunch of atomic-like systems that are ready to emit that same light. And this passing light will sort of wash the energy out, the stored energy out of this, what's called a laser medium. It'll take all those, it'll bring them, cause them to stimulate, to amplify the passing wave. And what went in as a wimpy wave comes out as a giant wave. Is that okay? I mean, there are so many kinds of lasers, finally. The basic idea, though, is you start with one wave that, we'll talk about where that wave comes from. I mean, approximately it comes often from the laser medium itself. You start with one wave, a little one, just one photon. It comes through and it causes all the other excited systems, excited meaning that they're not in their lowest energy state, they have energy extra already stored in them for some reason, and they're ready to duplicate that wave. They can not only, they've got to be able to duplicate its wavelength and everything else about it, like which direction it's heading. If they're lined up wrong so they cannot duplicate that direction, they're just let it pass by. But if they can duplicate it, they will. And actually, the stronger it gets, the more likely it is for them to duplicate it. The first few duplications is proportional to the number of photons in the wave. When it's only one photon, when it's brand new, fresh, the duplication factor is only 1. But if it's been duplicated 1,000 times, the chances that they'll duplicate it is now up to 1,000. So it goes up very fast. And so oftentimes a laser will have lots of excited systems in it. And when I say systems or atomic-like systems, often it is atoms. The original lasers, a lot of them were just atoms in a gas. Neon, for example. The first laser was a helium neon laser. Neon was what gave out the light. Helium was in there to help give neon the energy to start with. Do I have a helium neon laser up here? No. Anyway, you had lots of those excited states there in real atoms. But as time went on, they made other systems that are atom-like, but aren't, strictly speaking, like free atoms. For example, oh gosh, that's a cheat. This is this red laser pointer here, that is light being emitted by atom-like systems in a diode. That's a laser diode that's emitting that green light. So it's one of these, it's like a light-emitting diode, but instead of just letting every little particle, the electrons are dropping from conduction levels to valence levels, and they do a little sort of atomic jig around the positive charge area that they're going to try to settle into and fill. They circle it for a second, and then they settle. And in the act of settling, it's like an atom going from one orbital to another. Off goes a particle of light. And in this case, it emits red light. And in a red light-emitting diode, it's every photon's independent. In this, they made a very compact light-emitting diode, really tight. So they got incredible density of excited atom-like systems ready to emit light. And instead of just going willy-nilly, everyone on their own, they actually start duplicating one another's photons. And you get this massive giant wave comes roaring out. Questions so far? Things I've left untended to. So that's the radiation that comes out of a laser then, because it's duplicates of one initial photon, is coherent. It's described as coherent because all the photon, basically it's one enormous giant copy of that initial photon. It has all the characteristics of that initial photon, including all its wave characteristics. So it's a giant wave based on that first one that they started with. And it's got interesting interference effects as a result, which is part of what I'll show you in a second, having talked it all to death. This is sort of the continuation of the flashlight question. The flashlight question is sort of stupid. It says that, can you see interference effects with a flashlight? And the answer is yes, but they're pretty wimpy. This question is, can you see interference effects with a laser? And the answer is yes, and they're really intense. And so I'll show you some of them. Do I want to show this first? Not really. This is unimportant. I can turn this off for a second. Let me just show you. Gone. All right. So some interference effects with the laser, just for fun. If I chop, so this is my laser pointer here. If I chop that laser, the other one's brighter. This is two colors. Ooh, okay, green. Okay, so if I chop that wave, first of all, it's a small spot, which is already kind of interesting. It's hard to make a small spot with a flashlight. How did they manage to make it so small? Well, it turns out that because it is a single wave, they can manage to really manipulate it well in a way that you can't with light from a flashlight. In a flashlight, all the waves are going a little bit different. There are different colors. It's kind of a mess. And using refraction and reflection and stuff, you just can't make it very small. It's kind of limited. But with this light, because it is one giant wave, you can manipulate it very well with like a lens. You can get it aligned so it goes really in the same direction within the limits of the world of waves. And if I set it through, this is a mesh. So this is a screen for number 200 mesh screen. If I send the light through the mesh, can you guys see that it's broken up into a bunch of little pattern? Those are little interference. That's the result of interference effects, where I've chopped the wave up and then I overlap it again with itself from several different sources, and it ends up as a lot of separate dots. I can do this now. Let's see. There's another green laser over here, and it's going to appear on that screen on the right. And just so everybody can see it, I can put it up on the center projector. It is, yes. You should be able to see it up here. And yes, okay. So what this is doing at the moment, this is two slits. There's so many different patterns here. I'm going to go over to this thing. There, okay. What's happening right now is the green light, which is a single beam, just so you know that it's really just one light. There it is, that's the dot. Okay, so it's just a laser pointer that Allen gang ripped apart. And here now I'm sending it through a series of slits which block parts of it. And the wave then gets chopped up into, given how big the beam is over here, it's hitting maybe 10 of those slits. It's going, like going through a Venetian blind or something like that. And those little wavelets, what's left there, because it's one giant wave that had parts of it chopped out by the black stripes. And the pieces that are left interfere with each other. And they interfere constructively or destructively. And wherever it's dark, these points, that point, you see, where it's dark, they're interfering destructively. So zooming across the room, as I'm here in these beams, there are waves here that are overlapping at that point, but they're out of phase with one another. The electric fields, which are now strong, because it's one giant wave, they have big electric fields, and they're overlapping badly here so that they cancel each other. But right at the bright spots, they overlap constructively. Those are the angles at which, if you watch the waves trying to travel different distances from these different slits, they pile up and work together. So that's one example of interference. Where I put the laser pointer? I leave everything everywhere. Where did I put the laser pointer? Oh, there it is. Okay. Another example of this. I can stop that guy for a second. And when I was showing you the interference effect, when I was showing you the spectra of various discharge lamps, like the neon lamp, we were looking through a camera, not quite at the lamp, but rather at an interference pattern coming from the lamp. And the interference was produced by this little slide, which is called the diffraction grating, and looks very much like the surface of a CD or DVD. You know, if you look at a CD or DVD in sunlight, it looks brightly colored. That's interference effects. And that's in the presence of even ordinary white light, you get interference effects, or light from a discharge lamp. You get interference effects where each wave is interfering with itself. Lots of little waves, so the interference effects are kind of wimpy, but they're there. In this case, so this simply has lots of little lines on it. They are really close together. They're like wavelength distances apart, light wavelength. So they're millions of a meter, tiny. You can't see them, but you can see the interference effects that come from them. And if I shine laser light through it, it splits the laser light. So there's green light being broken up into 3 spots on the front screen. The middle one is the main spot. That's the light that goes straight through, and it goes through all the slits and travels the same distance and hits that spot. And on the right, that spot on the right is the light going through the slits, and with each slit toward the right, it travels one wavelength less. So at that spot and that spot only, all the waves that make it through the diffraction grating experience constructive interference only there, because at that point, if you can picture all the slits, here's a slit, here's a slit, here's a slit. The light that makes it through, this one has to travel farther than this one, because this one's got a little bit of a head start. It's a little too hand wavy. But they all manage to travel such that their waves are the same. The electric field phase is the same over there. Over here, it's the reverse. But the different colors experience interference, those constructive interferences at different locations. So this is green light, and here's red light. Because the wavelength's longer, the angle at which the light swings out to make those interference spots is greater. So here, I can do the 2 colors. And there you can see green, because it's got shorter wavelength, reaches the constructive interference spots closer to center than the red light does. Is that okay? Anyway, so they're giant. Most importantly, they're giant interference effects. You can't do this kind of thing with a flashlight. If I shine a flashlight through this slit, You know, it's just a mushy white spot, nothing much special. There are a little bit of fringes on the left and right. It's only with this coherent laser light that you get those interference, you know, serious interference effects. Is that okay? One other effect I wanted to show you that's over, I'll put it over there again. Is that true? No, I think it actually goes on this screen. So let me turn off the side projector for a second. We'll go all dark. There is a spot already visible on that side screen. Let me dim the lights. Come on, go darker. See that? You see that spot over here? Right there, that guy. That is the light from another laser, this guy over here, going through a pinhole. And the consequence of going through the pinhole is that you chop off the parts of the wave outside a very small region. So you're only allowing the very center of the wave to go through. And remember I talked about the other day that if you look, for example, at an electron in an atom, which seems like has nothing to do with this light. It does. I talked about an electron in an orbital of an atom. And I said that if you just leave the atom alone, the electron is all around the nucleus of the atom. It's a wave that lives around the entire thing. Don't pin it down. If you don't pin it down, if you don't go looking for where is it located, it will occupy this orbital very happily and stay there all day. If you do pin it down, you go in there with your microscope, of the right kind of microscope that you can see this, and you locate it there. It's within this little teeny subdivision of the atom. You can locate it, and you'll find, oh, it's there, but you will have chopped the wave off. And the wave outside that little detecting region is gone, and all you have is this very sharp wave that you have truncated. You killed off everything outside it, and it's now got sharp edges, among other things. And as the wave now evolves in time, which it will, if you let time continue, it won't just sit still anymore. You've pinched down on where it's located, and you have therefore increased its energy. And you've given it all kinds of trouble that will subsequently mean that it will fly apart, and a lot of it, in all likelihood, it will leave the atom as a result of having been pinned down. It sprays outward because you located it. Is that okay? I mean, it's a crazy notion that looking for it really changes it that much, but it does. This is the same sort of thing. If you send that light, which was going perfectly happily, that would have gone perfectly happily across the room as a relatively modest-sized dot like that's what it wanted to do. But if you truncate it by sending it through a pinhole and chop off the edges, yep, you know where it was located, briefly, but you mess it up. And instead of going as a very narrow light pattern as it used to, it's suddenly it spreads out. You pin it down too much. And if I go full dark, supposedly we can see circles around the center. Let's try that. Yeah, can you see the circle around the center, the fringe? The mathematics of that are interesting, but I can't go there. So it's got a central dot and then rings that go out. And that's all related to, that's the wave spreading. It shares a lot in common, I'll come back with light, with if you drop a stone in a pond, you make the ripples go out. It's got the same rippling effect. We've pinned down the light, and it's rippling outward. All right? What else do I want to? A consequence of this. Why tell you that effect where the light spreads badly after you pin it down is associated with microscopes and the whole idea of microscopy and trying to see things that are very small. If you go trying to look for something that's small on the order of the wavelength of light, or smaller, you go look for a virus through a light microscope. You can't do it for the same reason. It involves pinning the light down into too small a spot. And when you do that, it just spreads like crazy. So you can't, the wave nature of light prevents you from really noticing structure that's terribly small. In order to see things sort of on the atomic size scale, which is way below the wavelength of light, you have to use stuff that has wavelengths on the atomic size scale, like the wavelengths of electrons that are moving. So electron microscopes work because the wavelength of an electron that has any decent energy is pretty short. And so you can go looking for little stuff. X-rays work. X-rays and gamma rays too, although they're just harder to work with. All right. Anything else I wanted to say? Oh, just a few details to say about lasers themselves. Let me get this back, mess up everything. Got too much light as usual. Can't see anything. Lasers generally start with what's known as a laser amplifier. So you have a laser medium, which is some substance. It can be a gas, it can be a solid, that contains atomic-like structures that you can pack full of energy, that you can put them in a situation where they have the equivalent of orbitals, and they're not in the orbitals they would normally be found in. They're in excited orbitals, extra energy in them. And that can be done with flash lamps or chemical reactions, running electric current through the thing, all sorts of ways in which you pack it full of energy, and you make it so that it's capable of emitting light by these radiative transitions, that the electrons will go from the excited orbital to the lower orbital and emit light in the process. So you get it all ready, and then instead of waiting for the light to come out spontaneously, you trigger it. You stimulate that light emission by sending the right light through, and it gets copied. Zero-graph, it's like zero-graphic copiers, although completely different physics. And out comes a much brighter pulse of light. Okay? So where do you get the original light from? The classic way to do it is to put mirrors around the laser medium. So it sees itself in the mirror. And what happens is that if you wait a little while, one of these excited atomic-like systems in the laser medium will just, by chance, send its light backwards, hit the mirror, and go back through the laser medium. And when that happens, the laser medium gets a passing wave of the type that it likes to duplicate. And it starts duplicating. And if you put the laser medium between two mirrors, the light goes back and forth, and with every pass, it gets duplicated more. And eventually it gets duplicated. Basically, it reaches a point where it can't get duplicated anymore because it's just sucking all the energy out of the laser medium. If the energy is being resupplied, then you sort of reach a steady state where you hit a maximum. I should also say that the mirrors are not perfect. If you use perfect mirrors, yeah, it'll work, but the light will never come out, which is boring. Yeah, it's bright inside, but nobody notices. So what they normally do is they use a semi-transparent mirror. So one of the mirrors, and you're used to semi-transparent mirrors like the funny sunglasses that have look like a mirror on the front, but you actually can see through them. They're partially reflective, partially transmitting. And so you use the same thing in these lasers. How much of the light you want to let through is, you can figure it out, but it's not trivial to figure out what you want. So in a laser like this, I'm going for the red ones. So the red one, that is a light-emitting diode that's been shrunk down to tiny size so that it's really dense with excited atomic-like systems. And it's got mirrors on each end. One mirror is essentially perfect, and the other mirror is slightly leaky. And you're seeing the light from that slightly leaky side come on out. Okay? One thing, I keep going for the red one, not the green one. This strange device has two laser pointers in it. It's got green and red. The green one, and why don't I keep talking about the green one? The green one is a more complicated device. it is actually an infrared laser inside this device. It makes photons of light you cannot see, which sounds pretty useless. It's based. What they do is they send that light through an optical crystal, what's known as a nonlinear crystal, that takes the giant wave passing through it and responds to it in a weird way that doubles the frequency of the wave. And so in goes a wave in the infrared, and out comes a wave that is in the visible, green at 532 nanometers. It's actually doubling the frequency of the wave, and then consequently, since frequency and color go together, it comes out as green light. Another way of thinking about it is it's tacking two photons together to make one. One photon carrying twice the energy and therefore having twice the frequency. So the green laser pointers are special. Yeah. Is there any way to look at infrared light? Both. Yeah, so infrared light, there are sensors that see infrared light. There are all kinds of different devices to do this. They're actually pretty useful. The ones that see far infrared, thermal light, the light that comes off of us and things in this room is pretty deep in the infrared. It's not close to red. It's pretty far out there. And there are devices that see it. The best ones are semiconductor devices. Remember, semiconductors, the ones that emit light, it's one of these drawings. I can go back there. Oops, killed it. Remember this drawing from last time, that if you have a semiconductor and if it's cold and if it's dark and it's a pure semiconductor, all the valence levels are full and all the conduction levels are empty and it does not conduct electricity, right? But if you expose it to heat or light, you can promote some of those electrons. You can boot them up from the valence levels into the conduction levels, and suddenly they conduct electricity. So this is the drawing that here is drawn as a photoconductor. Here's light coming in, causing this thing to begin to conduct electricity. And I remarked that this is how xerographic copiers work. That special coating on a xerographic copier is such a semiconductor device that when exposed to light, it conducts electricity. So far, so good? If you make the band gap between the conduction levels and the valence levels very small, infrared light is enough to promote electrons from the valence levels to the conduction levels and allow it to conduct electricity. And so the fancy cameras, I mean, these are $15,000 type cameras, have an array of, first of all, they're based on semiconductors that respond to infrared light. They only need tiny amounts of energy to become conducting. And then they have whatever they need to make an image and to show you the image. So you can see in the infrared. Just pitch dark, and you look around, you see thermal. You see the glow that comes off of things that are warmer, for example, than the rest of the room. So people would glow brightly as viewed by a device that sees infrared at the 5 or 7 micron wavelength range, which is way longer than visible light. Is that okay so far? So infrared imaging. To see near infrared much easier. You use the same stuff that operates in your cell phone camera. Your cell phone cameras, the imaging sensor in there is typically silicon, and silicon responds to light from a little into the infrared all through the visible. It's actually very good in the infrared, and so it can see in the infrared. They actually have to put filters in your cameras and stuff to keep it from seeing the infrared, because things will look weird. And first off, it sees things that maybe people wouldn't want to have seen, because looking in the near infrared, stuff looks different. And they don't want, they want you to see what you're used to seeing, so they block off the infrared. The fact that the thing can see the infrared, they make it go away. Ultraviolet, seeing the ultraviolet, should be technically pretty easy to do because there's a lot of energy in every photon. I can't think of anybody who makes ultraviolet imaging devices, though. It's kind of what's there to look at. Is this okay? So lasers then, copying a single initial wave. You can make more sophisticated lasers. You can copy 2 initial waves. You can copy waves that are complicated already to begin with. And yeah. All right. Where we're going to go next is cameras. And just to sort of get you started with cameras. So far, we've make light, you can see light just as a glow. What if you want to actually see the pattern of light, a pattern of light that corresponds to the to where that light came from? So that instead of just seeing, like the room lights are just illuminating something. So if you just hold out a sheet of paper, for example, it's heavy. So if you just hold a sheet of paper out, obviously it's being illuminated, but you don't know what that, what was it up there? What did that look like up there that is illuminating the light like this? You can get a little bit of information by just simply putting if I put my hand in front, you can see the shadow's got a complicated pattern to it. So there's something about the direction in which the light's traveling that can give us a little information about what's up there. But if you really want to know what's up there, you go to a lens. And if I hold the lens out here, can you see the patterns showing up here? Yeah, I have to focus. This is focusing. So if I focus it right, we can see very much the shape and structure of the light source itself. And the physical phenomena that are involved in creating this, which is called a real image, because you can put your hand in it. It's real. You can touch it. That image is formed by light passing through this lens and bending the old-fashioned way by refraction. Remember refraction? This, unlike a window, is not flat. It's curved. And that curved character to it bends the light in different ways for different places on the surface of the lens. And it can do tricky things, like you can take all the light from one special spot on that light. It can bring all the light that would normally just hit all over the place, all over a big surface. It bends all that light from that one spot back together and lets it hit one spot on the sheet of paper. So you get light from one corner hits here, light from the other corner hits here, so on. Every portion of the lamp illuminates a different portion of the sheet of paper. So you see the lamp. You see an image of the lamp, that real image. Just for fun, what's the opposite? What's the alternative to a real image? A real image occurs when light goes through the lens, forms a pattern of spots that correspond to its source. A virtual image is where it occurs. A virtual image is, and I'll show you in a second. Okay, I'll show you right now. You're looking at a virtual image now of me. Many differences between a real and a virtual image. A real image is out here. You can put your hand in it. It's on the other side of the lens. You can put your hand in it, and you can touch it. It's upside down. So the portions, if I take an image of one of you out there, your head will image down below and your feet up above. So real images are inverted. Virtual images are not. So this is a virtual image. It's upright. The image, if you were to take your eyes and focus on it and try to figure out where this distorted version of me is, it's actually behind me. It's not on the other side of the lens at all. So light from me forms the image on the same side of the lens as me, and it's behind me, and it's bigger. And this is magnifying glass stuff. And if I go too far away, so there's a transition between, if I go farther and farther, I'm about there. My arms aren't long enough. I can't go quite to the distance at which there's a catastrophe, and then the real image starts forming instead of virtual. Anyhow, we'll look at that next time.